Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation, Reduction, and Carbon-Carbon Bond Formation Applications in Organic Synthesis, taken by Professor Yashwant D. Vankar from Department of Chemistry, IIT Kanpur. And my name is Sri Lakshmi S. I am a PhD scholar in IIT Bombay. So this is our third tutorial session. So in the last two tutorial sessions, we have been discussing the week 1 lecture as well as the week 2 lecture, and along with that we have solved several problems. In the first week we have solved week 0 assignment problems, and in the second week we have seen several examples related to the week 1 and week 2 lecture contents. So today we will be firstly starting with the week 3 lecture contents, then we will move into the problem discussion. So in the week 3 lecture, we started with in the first lecture, which was lecture 11, we started with this iodobenzoic acid mediated oxidation. So we started with this iodobenzoic acid mediated oxidation. So this is the structure of iodobenzoic 2-iodoxybenzoic acid. So this is the structure of 2-iodoxybenzoic acid. And this the problem with this reagent is that it is insoluble in many organic solvents, but it is soluble in DMSO, and therefore in DMSO we can use it as an oxidizing agent at room temperature itself. So since it is an oxidizing agent, the primary transformation it does is the conversion of alcohols into aldehydes. It basically oxidizes alcohols into aldehydes. So as we can see here, this is the structure of this iodobenzoic acid, iodoxy 2 iodoxybenzoic acid. So what is happening is that first our substrate, which is alcohol, so here that it is attacking over, yeah, 1 second. Okay, so this our alcohol substrate. So here we have taken methanol. So that will be attacking over this iodine sender and it will form this intermediate. Then what is happening is that this one of the proton will be taken by the oxygen and that bond will shift over this and this will come over this iodine. So this will be the byproduct which we will be getting, and the oxidized product which is formaldehyde. So basically we have oxidized methanol to formaldehyde using iodoxybenzoic acid. So, as we saw in the mechanism, since this I double bond O group is out of plane, the alkoxy group cannot be in plane with the I double bond O to form a 5-membered cyclic transition state. So, here, as we can see, this I double bond O is out of the plane. So, here it is not possible to form a 5-member transition state in this intermediate. So, this basically goes through a twist type of mechanism. So I am not going into any detail because we have already seen this in the lecture. And other forms of this IBX involves this silica gel supported hydroxybenzoic acid or polystyrene bound hydroxybenzoic acid. And here are some of the examples for the transformation where this alcohol is converted into this aldehyde, and then this is converted into this two molecules of this uh, cleaved product. Actually it is forming over this condition. Then here we can see one of this hydroxyl group is converted into this ketone, and here both are converted into this, and here we are getting mixture of product where both alcohols are converted and here only one is converted. So here why only this particular alcohol is converted into this ketone? It is because of this proton. So here there are no such protons available. So that's why this alcohol is remaining intact, and while this alcohol which is having an alpha proton is getting oxidized. Then so here we see this diol is basically getting cleaved, so oxidation is also happening, and this carbon carbon bond cleavage is also happening under this condition for this type of diol. So here the mechanism goes like this. So firstly, the dimethyl sulfoxide, which is basically the solvent which we are using, will form an intermediate of this kind with this hydroxybenzoic acid. Then our substrate, the diol, so the one of the hydroxyl group of that diol will attack over that iodine. This OH will leave, and then another OH will also attack over that iodine, so it will form this kind of an intermediate. Then what is happening, this bond will shift over here, this will come over this, and this will come here. So basically this bond is getting cleaved. So that's how this alpha hydroxy ketone will be like, that's how this will be forming, and in a similar mechanism this will also be forming from this kind of diode. So here also we can see there is no alpha proton. Here also we can see only this hydroxyl is having this alpha proton, the other one is remaining intact. Now this another application of this hydroxybenzoic acid comes for the conversion of alcohols to enones. So this is an alcohol, so it can be converted into this alpha beta unsaturated ketone by using this IBX at reflex condition. So here we can see this alcohol. If we are treating with two equivalents of IBX, we are getting this alpha beta unsaturated ketone. But if we are using excess of this IBX, we are getting both sides this double bonds. So it just depends on the amount of IBX. So if we want conjugation at both sides of the ketone, we have to use excess of this IBX. So that mechanism goes like this. So firstly, the basic mechanism where this hydroxyl group is converted into this ketone by the IBX. So this can exist in this enol form as well. Then this lone pair of oxygen will attack over this iodine. This will shift over here and it will form this intermediate. Then what is happening? A proton from here, yeah, so a proton from here will go and that bond will shift over here, and this will come over here, and this bond will break, OH will leave, so water molecule will be eliminated, and this will be the byproduct, and we will be getting this alpha beta unsaturated ketone. Then this is another example where this ketone is converted into this alpha beta unsaturated ketone using this IBX. So another mechanism which is reported by Casey Nicholas group for this type of reaction is given here. So there what is happening, firstly this hydroxyl group is getting proton like here, yeah, so a proton will, a radical, this bond is cleaving, so a radical will be generated here and a radical will be generated here, and this lone pair and this will form a bond over here with a positive charge on this oxygen. Then here this bond will migrate to here and this double bond will be formed here. So mm, yeah, so this electron will be given by this IBX, this radical form of this hydroxybenzoic acid. So that will result in this compound. So what is happening to this reagent, as we can see, as this electron goes and it is taking this proton from here, it will form this particular intermediate, and then this will take another proton which will form this intermediate, and then this elimination of this water molecule will give this iodosobenzoic acid as the byproduct, and we will be getting this product. So mechanism is, this is little bit confusing, I think this will be the better mechanism for the understanding, but this is also reported. Then another reaction is this Doben-Mignon rearrangement. So we have already seen this kind of reaction by using this PCC and PDC chromium-based reagent. So similar reaction is happening with IBX also. That is for the transposition of ketones. Or we are starting with this. We will be using some lithium, like any alkyl lithium, so it will undergo 1 to addition over this ketone to form this alcohol. Then similar mechanism like in type of mechanism which we saw for this PCC and chromium based reagents, same mechanism happens here for IBX also. So this sigmatropic kind of rearrangement will happen, and this transposition will happen for this alcohol, and it will be coming as this alpha beta unsaturated ketone. Then I guess maybe we can go to the some problem discussion. Then we will discuss that remaining week lecture contents. So we will start with this assignment questions directly. Um, the solution is already there for week 1 and week 2 assignment questions, so we will go through that first. So if you have any doubts or questions regarding the answers of each question, we can go through that. So the first question of week 1 assignment was the compound that permits one oxidation of an alcohol is. So here are four reagents given here, so which will be the correct answer? It would be good if any of you can respond. Can any one of you try which will be the correct answer? Afrin, Nikita, Shweda, any of you can answer this? Okay, we will go to the answer. The correct answer is option 4. So, what is happening? This is swan oxidation. So, basically, for swan oxidation, we are using DMSO, oxalic chloride, and triethylamine as the reagents. And one of the condition for the swan oxidation is that for swan oxidation to take place, one hydrogen must be present at the sp3 carbon attached to sulfur atom of the sulfoxide. So, as we know, in the case of DMSO, we have two methyl groups, which both of which are sp3 carbons present at which is having hydrogen atom, of course, attached to the sulfur atom of the sulfoxide. If we see the mechanism of the reaction, so that hydrogen is playing role by, we can say, intramolecularly. Actually, that hydrogen is helping in the mechanism of this reaction. So that hydrogen will be taken by the base, and that will be shifted over, and that's how that rearrangement. I am not going into the mechanism, already we have seen in the last classes. So that hydrogen plays crucial role in the mechanism of the reaction. So that's why only such sulfur compounds can participate or can start this swan oxidation reaction. So if he see here, this is having diphenyl group, this also having diphenyl group, this is having phenyl and this vinyl group, and this is having one phenyl and one methyl group. So only possibility is with this option 4, which is having this methyl group. So proton can be taken from this methyl group of this compound. So the correct answer would be option 4. If you have any doubts, you can ask. Okay, then we will move to the second question. Cornblende oxidation involves First option is a SN2 reaction of DMSO on a substrate having a leaving group. Second option is reaction of dimethyl sulfide with N-chlorosuccinimide. Third option is an SN1 reaction of DMSO with a tertiary alcohol. Fourth option is reaction of dimethyl sulfide with an epoxide, which will be the correct answer.
Option number first.
Yes. So what is Kornblum oxidation? Like which reagents we are using for Kornblum oxidation? Do you remember? So for Kornblum oxidation, we are using a DMSO and a base under heating condition. So that base can be K2CO3, like potassium carbonate or sodium bicarbonate. So first option is the correct answer, and SN2 reaction of the DMSO on a substrate having a leaving group will be taking place. So this sulfonium ion intermediate will be resulting, which will lead to the formation of our oxidized product. Now, the third question, the incorrect statement with regard to Moffat-Pfirzner oxidation. First one is DCC is used to activate DMSO. H3PO4 acts as an acid catalyst. Dicyclohexylurea is formed as a byproduct. The use of moist DMSO is necessary. So, which of this is wrong? So, as we know, for Moffat-Pfirzner oxidation, we use DMSO with this DCC, that is hexyl carbodiamide, in the presence of catalytic amount of H3PO4. So that was the first oxidation which was reported using this DMS. Then after that, several modifications came, like Barton Swan oxidation, the Kornblum oxidation, everything came after that. So which is the wrong statement for Moffat-Pfirzner oxidation? So the correct answer is option 4. The use of moist DMSO is necessary. So it's not like that. We need to use like moisture-free condition for carrying out all this oxidation reaction. So that is a wrong statement. The use of moist DMSO is necessary. So in all the mechanisms which involve DMSO, the first step is usually an electrophile or an electrophilic source will be there. Here it is DCC, or in some cases it is oxyl chloride. Some cases it is pyridine, that SO3 intermediate, acetic anhydride. So first step is the same for all, that is this DMSO is activated using whichever electrophile we are using. And Then in this Moffat-Pfitzner oxidation, this H3PO4 acts as an acid catalyst, and since DCC is used, so this dicyclohexyl carbodiimide is used. So whichever reaction we are using that DCC, the byproduct will be usually this dicyclohexyl urea, and that we saw as one of the drawback of this reaction. Because of the formation of this dicyclohexyl urea, the purification of this reaction becomes difficult. So this is a very, like, it is very difficult to remove this dicyclohexyl urea from the reaction mixture. So that's why then several modification came, including Swan oxidation for this Moffat-Pfitzner oxidation. So the first three statements are correct. The last one, the use of moist DMSO is necessary, that is the wrong answer, wrong option. So moving to the fourth question. So here a reaction is given. This um, deuterated alcohol, which is treated with this dimethyl sulfoxide DMSO, oxyl chloride, and then triethylamine. So this is one oxidation condition. And what is happening? Which will be the major product here? And we have to see the temperature also. It is also maintained minus 78 degrees Celsius to minus 60 degrees Celsius. So if for one oxidation condition, the temperature is correctly maintained, the formation of side products will be less. So which would be the correct answer for this?
Option number 3.
We will see. Can you tell why you told option number three? So, as I told earlier, this mechanism basically involves firstly this um whatever that sulfoxide compounds which we are using, it should have an alpha methyl group attached to this, or methyl group, like some protons or should be there in the molecule or in the group attached to the sulfur. So here it is there. Then what will happen? First, that proton will be abstracted, and in an intramolecular fashion, then the next proton or deuterium will be abstracted from the alcoholic part. So here we have this deuterium here to be taken, and that will be taken in an intramolecular fashion. So this will go and we will be getting the corresponding oxidized product, and this would be taken by this DMSO part. So DMSO is basically this S double bond O, this one, CH3 dimethyl sulfoxide. So if one of the proton goes here, and in place of that it is abstracting a deuterium or proton whichever is present from the alcohol. So here it will come this deuterium. So that's how this is formed, methyl SCH2D. This will not be there. This will be the byproduct. Usually if we are using um, this like here, if proton was there, our byproduct will be dimethyl sulfide. Is it clear? If you don't understand, please feel free to ask. Okay, then we will move to the fifth question. The following molecule which cannot undergo Pumara rearrangement is or are. So here are four compounds. So we have to first know what is Pumara rearrangement. So it is one of the side reactions which can happen in the case of Swan oxidation if we have not maintained the temperature properly. If we have, like, I told earlier, the temperature should be in the range of minus 78 degrees Celsius to minus 60 degrees Celsius for the swan oxidation to take place smoothly. If we have, in case we are not maintaining that temperature, this side reaction can happen. And this type of rearrangement is observed in case of sulfur compounds as well as selenium compounds also. So here, which molecule or molecules cannot undergo this type of Pumara rearrangement? So the here the correct answer is answer this third option and fourth option. So as we said earlier, in the case of swan oxidation, for this Pumara rearrangement to take place also, there should be at least one hydrogen at the sp3 carbon alpha to the sulfoxide moiety to get a sulfonium ion. So here we can see this proton is there, and here also this proton is there. Then here there is no such proton. Here also, as we can see in the alpha position, two methyl group and one is phenyl ring. So there is also no alpha proton. So Pumara rearrangement cannot be taken place. So in Pumara rearrangement, what will be the product we will be getting? This kind of R CH2O CH2S Me. So this type of a complex we will be getting in the case of Pumara rearrangement, which is one of the side reactions that can happen for swan oxidation. Now the next question, the major product that will form in the following reaction. So here the sulfoxide compound is heated. So which compound can be formed here? So as we can see, all are olefins. So elimination is taking place, but which elimination will be more favored and which will be the product? Any idea? So here the correct answers are option 2 and 4. This one and this one are possible. So what is happening here? This phenyl sulfone is getting eliminated through a 5-member transition state leading to the formation of olefin.
Ma'am, can I ask one question?
Yes.
Ma'am, it's not about this question.
Huh.
It's like basic, but I don't understand. Like in these types of questions, like major compound and what will be formed,
Yeah.
I'm not able to understand how to handle this. What steps should be first taken in consideration, and then I should move in which way? Can you please just once tell me that format?
Yeah, so first thing you have to do is for this type of question is eliminate the options which is not at all possible. So that is
Hmm.
the first thing we can do. Then we have to see, okay, from the other three options out of our knowledge, which can be the favorable one. So here, as we have mentioned here, this option one is not possible as the sulfoxide oxygen carrying negative charge will face repulsion from the electrons from the OMe oxygen. So here, if like here this proton
Hmm.
is going over here and this is getting eliminated, so this should basically take this proton, right? So this O minus
Hmm.
should take this proton, but this OMe, this methoxide group is already electron rich in nature, so this
Hmm.
cannot come at this place and take this proton because of the electronic repulsion.
Hmm.
So this is
Yes.
the least possible answer, right?
Hmm.
And then compare then the other three options. So if we leave this one, so this is a possible answer, but if we see here rather than that proton elimination, what is going? OMe is going. So is that possible? Because what will happen is this basically in this elimination, this bond will polarize and this O minus will take up something positively charged, right? So here it is taking a proton, but this OMe is already OMe minus it is. So is it possible to take this methoxy group for this sulfone? You understood? So here is already hydrogen
Hmm.
and this OMe is missing. So we know
Ah.
this OMe is negatively charged, right?
Ah.
And this group also, that is
Ah.
S O minus and here
Hmm.
plus. Then
Hmm.
phenyl group and other group is also there.
Hmm.
So whether it is possible for this negative charge of this oxygen to take up this
Hmm.
OMe?
नहीं नहीं
No.
रिपल्शन होगा
Yes.
फिर.
So only possibility is proton abstraction and then
Hmm.
undergo elimination. So this option is
Hmm.
also not possible, right?
Hmm.
So from the other two options, anyone can be possible. Both are just elimination. Here also that proton is there. Here, like if it is taking one second, yeah, if it is taking proton from here, we will get this option 4, and if it takes this proton from this methyl group, we will get this option 2.
Hmm.
So the thing is that without directly going into the correct answer for this multiple choice questions, we can what we can do is just cut out which is not possible. Then we will have less things to remember and confusion will be much less. Okay.
So, ma'am, I mean to ask that not in this particular question, then in any question which comes in this format,
Hmm.
the first thing is we have to eliminate based upon their stability,
Not
like
stability.
that.
So, first thing is that if a question comes, the basic
Hmm.
things in that question we should be knowing. Like, for example, if it is about swan oxidation, so we should
Hmm.
know what is swan oxidation, how it
Hmm.
happens, and what are the
Hmm.
intermediates that is possible, the mechanism.
Hmm.
So, these are the
Hmm.
basic things which we should know. In the case of Pumara rearrangement, also same, we should know this
Hmm.
basic concept. Then
Hmm.
that concepts we can apply to this options and see
Hmm.
which is not possible.
Acha. Okay.
Okay.
Yeah, ma'am.
Yeah. So you are doing MSc?
Yes, ma'am.
Okay. Okay. So we'll move to the next question. The appropriate substituent X in the starting material leading to the product in the following reaction. So here this particular allyl group is attached to this position and any leaving group or any group is also there, which we are treating with MCPBA first and then heating. So as we can see in the product, an extra double bond came and this X is also not there. So elimination is taking place. So which group can be considered as this X, whether it is SPH, SIME3, OPH, or this SOPH? So have you seen this type of reaction? What will be happening first with MCPBA? If X is SPH, X is SIME3, X is OPH, X is SOPH, what can happen with MCPBA? So MCPBA, metachloroperbenzoic acid, basically we are using it for epoxidation reaction, or you might have heard about Bayer vinegar oxidation, or sometimes the other oxidation reaction. So its basic role is it is providing an oxygen. If it is epoxidation, or if it is Bayer vinegar oxidation, or any other type of oxidation reaction, it is basically providing an oxygen atom. Then in the second step, while heating, some kind of elimination is happening and this double bond is forming. So here, when this SPH is there as the substituent, so as I said, this MCPBA will provide an oxygen. So this SPH can be oxidized into this corresponding sulfoxide, that is S double bond OPH. So here this will be SOPH. Then so in the last case, in the next step, this elimination is happening. So this will come over here and this will go. So if it is any other of this, such type of an oxidation is not possible. Whether it be trimethyl group basically we are using for protection reaction, protection of alcohol, and OPH, it cannot be further oxidized with MCPBA, and SOPH, it is already in the oxidized form, so there is no use of MCPBA. So if it was SOPH and only heating condition, then this could be the answer. Like if this MCPBA was not an option, then this SOPH would be the right answer. But since first reaction we are using MCPBA and then only heating condition, so firstly SPH will be oxidized to SOPH and then elimination. This syn elimination will happen. Sulfoxide, this phenyl sulfone will leave and we will be getting this eliminated product. Is it clear? Okay, so we will move to this last question of this first week assignment. In the following reaction, although the starting ketone is racemic, it has a locked conformation with tertiary butyl group in the equatorial position. The nucleophilic addition of methyl magnesium bromide is highly stereoselective, leading to A as the major product and B as the minor product. Then the correct statements about the products are. So as we can see here, this particular cyclohexanone derivative we are treating with this methyl magnesium bromide, so this will attack over here and this will become alcohol, methyl will come. So This methyl can come above from the same side of this tertiary butyl group or from the opposite side of the tertiary butyl group. So this tertiary butyl position is equatorial already in the starting material, and that has not changed in both of the products. Only either methyl group can come from opposite side, then alcohol will move into the same side as that of tertiary butyl group, which will give this product, which is the minor product. And if it goes in the opposite fashion, that is methyl group will come from the same phase as that of tertiary butyl group, hydroxyl will go axial, which is opposite to that, and give this A. So the question is, A and B are both are optically pure. So this A and B both are optically pure, that is they are diastereomers, or diastereomers also, and not in racemic form. And A is optically pure but B is not. B is optically pure but A is not. Both A and B are racemic. Which would be the correct answer? So what is optical purity or racemic? What does it convey? What do you know about that? Any idea?
Comparative ratio of two elements present in a compound.
Uh,
The mixture compared to other.
you are talking about optical purity.
Uh,
Actually, what is racemic? That you say. Then we will explain optical purity.
Racemic तो
Have you heard about enantiomers?
हाँ, yes ma'am.
What is enantiomer? What are enantiomers? So, how these two compounds are related? Are they enantiomers or diastereomers?
For enantiomers, they should be mirror image,
Yeah,
but um, they are not mirror image because of the no, they will not be mirror image of
no,
each other.
because this is already fixed here. Only this center is
हाँ,
changing, right?
हाँ,
So these are, we can say they are diastereomer because one is fixed, only one
हम्म,
center is changing.
हम्म,
So racemic means if we have equal and opposite, like equal mixture of both the enantiomer. For example, if we consider this A, and what will be this enantiomer? Maybe we can call it A prime. So its enantiomer will be exactly the mirror image of this one. That
हम्म,
means this tertiary butyl group here it is equatorial. In the mirror image, it will be axial, and this position will also change. Methyl will go axial, hydroxyl will come equatorial. So that is the exact mirror image of this A, which is A prime.
हम्म,
So if it have this A and A prime together in an equal ratio, we will call it a racemic mixture of A.
okay.
And same with B also. If its enantiomer is B prime, which means in B prime, tertiary butyl is axial, methyl is equatorial, OH is axial. That is exact mirror image of this B. So, and if this B and B prime is present in equal ratio, we
हम्म,
will call it racemic mixture of B.
okay,
Now, optical purity means it is only having A. There is no A prime. And this also, it is only having this B. There is no B prime. Is it clear? So A and B are optically pure means A have only this stereochemistry. That is only compound which is having this tertiary butyl alpha hydroxyl tertiary butyl below, hydroxyl axial, methyl also methyl equatorial. Only it is having that mirror image is not present. Here also that mirror image is not present, only whatever configuration is given here that is only present. So that's what A and B are, both are optically pure. Now second option is A is like that but B is a racemic form, or B is not optically pure. It can be equal or some ratio of this mixture. Now the third option is B is pure, but A is having some amount of A prime which can be equal amount or more or less amount. Now the last option is A is also racemic. That means A is having equal amount of its mirror image also. B is also racemic. B is having equal amount of its mirror image also. Um, the concept is clear, or should I explain one more time? Okay, I hope it is clear. Now, if we go through the question, already it is mentioned, although the starting ketone is racemic, it has a locked conformation with tertiary butyl group in equatorial position. So, what does it means? So, just think your answer based on that sentence.
Option 4.
Yeah, so why? Can you explain? Okay, we will see. Correct answer is option 4. So here it is given the starting ketone is racemic. That means this starting material is having its mirror image also in an equal amount. So if we are starting with a racemic compound, always the product will be also racemic unless we are using some extra chiral sources like chiral auxiliary or something. Here only we are using methyl magnesium bromide and then hydrolysis. So in that case, whenever we are starting with a racemic compound, the products whichever is forming all will be in racemic. So this is racemic form, that is opposite enantiomer is also present. So this will be also having its opposite enantiomer in equal amount. This will also be having its opposite enantiomer. So the correct answer is both A and B are racemic. Is it clear now? If you find any concept which I told now as confusing, you can ask. So here the answer is already in the question. The starting ketone is racemic. So whenever the starting compound, starting material is racemic, unless there is no extra chiral source used in the reagent, the product will be also racemic. I think we can now move ahead with week 2 assignment also. Then, if time permits, we will continue the discussion on the week 2 lecture topics. So, the first question of week 2 assignment was the major product that can form in the following reaction. So, this particular alkene is treated with catalytic amount of selenium dioxide and tertiary butyl. I think it should be hydroperoxide. One more oxygen should be there, and H. In DCM at dichloromethane at room temperature, which will be the major product. So, if you have gone through the lecture videos, I think week 1 lecture in selenium mediated oxidation reactions, we have seen this particular example also, or a similar example. So for this SCO2 mediated oxidation, there are certain rules to predict the regiochemistry of the reaction. So we have seen like oxidation occurs at the di-substituted side of a double bond and provides a non-bridged alkynyl hydrogen will be taken. Then I'm not going into detail of that. Then another one was order of reactivity would be secondary will be CH2 will be greater than methyl group. Then only tertiary will be coming. And one among such rule was oxidation never occurs at the bridge head position. So it is a contradiction to Brett's rule. Brett's rule, it's basically that carbocation formation will not be taking place at the bridge head position. So one such rule for the SCO2 type of oxidation is that oxidation can never happen at the bridge head position. So if we see, the correct answer is option 4. So SCO2 is basically used for the oxidation of allylic position. So here allylic position means either this position is available, here this proton, or this position is available, or the another option is this proton. So if we consider this one and this one, it cannot be, these positions cannot undergo the SCO2 mediated allylic oxidation because of the contradiction to Brett's rule. So this one cannot be the answer. And this is like oxidative transposition. The position of alkene is not changing. So that type of reaction is not known with SCO2. So this is also not possible. Then the another two possibilities are option 3 and 4. So in 3, what we can see, in 3 what we can see is this allylic position is oxidized. So that is according to the Brett's rule contradiction. Other than that, it is favorable. Then in the last option we can see an elimination happened from one of the methyl group. It took proton and water molecule eliminated to form the alkene. And so as we said, one of the rule is this bridge head position won't favor this allylic oxidation. So another role is in the case of formation of this tertiary alcohol, elimination would be preferred more. So this tertiary alcohol will form, and that elimination of the tertiary alcohol can result in the formation of a tertiary carbocation, which is very stable, and then this elimination will give this alkene. So the driving force for this kind of elimination would be, we can say, the formation of tertiary carbocation. So oxidation at bridgehead will not occur, and other allylic position is tertiary. Moving to the second question, the major product formed in the following reaction. So this alpha beta unsaturated ketone is undergoing three reaction. First one is this phenyl magnesium bromide and copper bromide reaction. Second one is this trimethyl silyl chloride reaction, and third one is this palladium acetate and benzoquinone reaction. So can you tell what is happening in each of these steps? Okay, so the correct answer is option 2. So I will explain one by one step. So in the first step, what is happening? This phenyl magnesium bromide is there, but along with that, we are using this copper bromide also. So rather than this 1 to addition of this Grignard, Gilman reaction is taking place. So this 1,4 addition will be happening, and here phenyl group will come. So the correct, like in the first step, what we will be getting is, here ketone will come, and in this fourth position, this phenyl ring is coming. So that will be the first one. Then what is happening? Uh, like this will go through. So the intermediate will be like this 6. So this phenyl group will attack over this position. This double bond will come over here, and this will shift over this one. So it will be here phenyl group, and here it would be double bond. This double bond will shift over this position, and here O minus will be there. So in the next step, what will happen? That O minus will trap this trimethyl chlorosillyl group from this trimethyl silyl group from this trimethyl chlorosilane. So here, instead of O minus, in with the next reagent, it will be OTMS. OTMS is basically oxygen attached with this trimethyl silyl group. Then what will happen? Palladium acetate benzoquinone condition, oxidation is taking place. So oxidation means with this double bond, firstly palladium will coordinate, then it will undergo this type of an elimination reaction, OTMS, and this palladium will come over here. Here phenyl group will be there. So firstly palladium will coordinate with this double bond, and then it will migrate to one of that positions of the double bond, and then an elimination, like this palladium will take the hydride, and a beta hydride type of reaction will happen, and here double bond will form, and this will be hydrolyzed back to the corresponding ketone. So this will come over here, and then this is going here. So here also this will be double bond OTMS plus, then this hydrolysis will give the ketone. I will tell one more time. So firstly, this phenyl group will attack over this 1,4 fashion because of the presence of this copper. This is not simple Grignard addition, it is Gilman addition. And then this double bond will shift over here. This will go here, and this O minus will take up this trimethyl silyl group. Then this oxidation will take place, which result in the formation of kenone. Is it clear? Okay, now moving to the next question. In DMP oxidation of the following 1,2-diol, the major product that will form this compound is treated with this DMP. So which will be the product which we get here? So this we already saw in the starting of this class. With DMP or IBX, if we carry out this type of reaction, which can be the product? DMP is basically the acetoxy derivative of IBX to hydroxybenzoic acid instead of alcohol if there is acetyl group, that is DMP, desmartin periodinate. Both are hypervalent iodine reagents. Any idea? So here the correct answer can be either option 2 or option 3. So as we can see here, one of this alcohol is tertiary and the other one is secondary. So of course only primary and secondary alcohol can undergo oxidation. In tertiary, the no proton is there for oxidizing that alcohol into the ketone. So that is not possible. So this in the given 1,2-diol, one is tertiary and other secondary. With DMP, which is a mild oxidizing agent, secondary alcohol undergoes oxidation to form corresponding alpha hydroxy ketone. So this can be one option. Then we saw in the earlier example that the diol cleavage type of reaction is possible with this hydroxybenzoic acid or this DMP type of reagent. So that can give us this type of compounds. And in this also one alkene is forming, which is basically by elimination, but here for DMP is a mild oxidizing agent and no heating condition is mentioned, the formation of alkene is not possible. So this option 1 and option 4 can be ruled out. So two possibilities are either only the secondary can be oxidized into ketone, then tertiary will remain as such, otherwise a diol cleavage type of reaction can happen and form this compound 3. Moving to the fourth question, in a typical sulfoxide sulfonate rearrangement shown below, the correct transition state Ts is represented as. So this is like here this sulfoxide group is there, that is coming over this position. So this bond is migrating to here, and here S double bond O is there, but in sulfonate, as we can see, oxygen is connected to this position, so it is attacking through this oxygen at this position, and this is going here, and this bond is breaking. So this is forming. So this is basically an equilibrium reaction in which this equilibrium will be more favored towards the sulfoxide. So which transition state can be formed here in this reaction? So here the correct answer is option 4. So as I said, it is going through this type of mechanism. It will go here, this will go here, and this bond will cleave. And what is the difference between these transition states? So basic thing we have to consider is the geometry of the double bond is remaining intact. Geometry of double bond is not changing. That means this methyl and this phenyl group is in same position. So except in this option, in this also methyl is above, phenyl is above. Here methyl is below, phenyl is above. Here also we can see this methyl is above but phenyl is below. Here methyl is above, phenyl is above. So possibility is for this 1 and 4. So that is the first condition. This double bond for the sulfoxide sulfonate rearrangement, this double bond geometry is not changing. Now, if we consider the second factor, this is a basic factor which we can say. So, for this center, always in a transition state, six-member transition state, the bulky group will be preferring equatorial position over axial position. To minimize the steric repulsion or diaxial interactions, the bulky group will always prefer equatorial position. So, if we consider that isopropyl group is obviously more bulkier than the methyl group. So in this option, but isopropyl group is axially oriented, methyl group is equatorially oriented. But if we consider this last option, isopropyl group is equatorially oriented and methyl group is axially oriented. So here double bond configuration is also preserved, that is methyl and phenyl is in same side, and isopropyl group, which is the bulkier substituent, that is on the equatorial side. So this is the favored transition state. Option 4 will be the correct answer. Moving to the next question. In the following allylic oxidation with SCO2, the structure of possible intermediate. So this alkene we are treating with SCO2, tertiary butyl hydroperoxide. We are getting this product. So just we have to predict which intermediate can be favorable. So allylic oxidation is happening. This position is getting oxidized and hydroxyl group is coming over there. So through which intermediate we can get this product? So here the correct answer is option 1. So what will happen first is this intermediate will be forming. So this selenium will attack over this position. This double bond will shift over here and we will be getting this particular intermediate. Sorry, like this. Selenium cannot attack there. Double bond should go and attack. So this will go here and this double bond will attack over this selenium and we will be getting this intermediate. Then in the next step, what is happening? This oxygen lone pair will attack over this center. This double bond will again migrate to here and this will break and we will be getting OSC type of intermediate and then that will be converted into this corresponding hydroxyl group. So the double bond interacts with SCO2 forming carbon selenium bond. That will be the first step and then removal of allylic hydrogen next to the phenyl group in this case to form intermediates as shown in choice 1. So this I shown like in a concerted manner. Here they have explained it in a stepwise manner. First SCO2 form this carbon selenium bond, then this allylic hydrogen will be removed and this will attack over the center. Next question. The structure of a typical allylic sulfonate ester in sulfoxide sulfonate rearrangement, which is called Mislow-Evans rearrangement, is so which out of this compounds given here, which will be the sulfonate ester which we will be getting or that will be involved in this Mislow-Evans rearrangement? So here, as we saw in the earlier example also, in sulfoxide sulfinate rearrangement, this allyl sulfoxides will be in equilibrium, where the equilibrium will be more shifted to the allylic sulfoxide towards this allyl sulfinate ester. And if we remove this sulfur group by using any thiophile, we will be getting corresponding alcohol over that position. So that is the utility of this kind of sulfinate ester. So this would be the basic structure of that reaction. So as I said here, what is happening, if this is the allyl sulfoxide, this O minus will be attacking over this center, this double bond will shift over here, and this bond will break. So out of the intermediates given here, only option 2 matches with that. This is the starting material. There should be an OSR bond. So this is also oxidized product. These are highly oxidized. This is also oxidized product. So maybe we can say this is sulfox. No, here one extra oxygen is there. So these are neither sulfoxides nor sulfinate. So the only sulfinate here it is option 2. Now the next question, in the conversion of allylic alcohol 1 to another allylic alcohol 2 via a sulfoxide sulfinate rearrangement, Mislow-Evans rearrangement, the possible intermediates. So here this is converted into this one. So here at this position and CH2PH is coming. So they have given that it is going through this Mislow-Evans rearrangement, which is sulfoxide sulfinate rearrangement. So which among this given options can be the possible intermediates? So here the correct answer can be option 1 and 2. Both are the possible intermediates. So what will happen first is, firstly, this when we treat this with this PHSCl and triethylamine, it will form here this corresponding OSPH. Then that can undergo this sulfoxide sulfinate. So this is basically in the sulfinate form. Now this can undergo rearrangement into the corresponding sulfoxide. So that is this one. So previously we have seen the opposite, sulfinate to sulfoxide. As I said, it is reversible, exists in equilibrium. Sulfinate can also be converted into the corresponding sulfoxide. So this will be formed. So firstly this will be formed and then this will be formed. What will happen? This will attack over this center, this will migrate over here, and this bond will break. So from this intermediate is converting into this intermediate. That will give rise to this allylic sulfoxide. Then what will happen? A proton alpha to the sulfoxide. So a proton here at this center will be basic in nature because of the presence of, will be acidic in nature because of the presence of the sulfoxide group. So that will be eliminated. Okay, I am doing it in the wrong example. Okay, so here first OSPH will be forming, which is this one. So this will be, the starting material will be converted into this one. Then what will happen when it will come over here, that is this is coming over here, this will go over here and this will go over here, and at that same place we are adding this what this what we can say benzyl bromide we are adding in presence of a base. So this proton over this center, which is alpha to the sulfoxide, will be basic and that will be abstracted, that will be acidic and that will be abstracted, and it will attack this CH2, and Br minus will leave to form this intermediate. So that will happen through this, we can say. Here methyl will be there and here SO pH will be there. So firstly this will be converted into this and this will be converted into this one by sulfoxide sulfinate rearrangement. Then this proton is basic in nature, so base acidic in nature, so base will abstract this proton, and then while adding this one it will form this intermediate. Then what is happening? Then if we further undergo rearrangement, again this can undergo rearrangement like this can sorry, this mouse is troubling me. So this lone pair can attack again this double bond. This will come over here and this will break. So firstly, what we have seen is sulfinate is converting into sulfoxide. Then again the sulfoxide will be converting into the corresponding sulfinate. So here again OSPH will be formed. Then that OSPH will be converted into OH to form this compound. Is it confusing or is it clear? Should I explain it one more time? So first, it is like protection with triethylamine that will abstract the proton from this hydroxyl group and that will attack over this sulfur. So OSPH will be formed. This will be formed. Then in the next step, what is happening? This will attack over this double bond. This will come over here and this bond will break. So we will be getting this particular intermediate. So here will be S double bond O pH. So what happened? The sulfinate got converted into sulfoxide and double bond shifted to this position, and here will be methyl group. Then what is happening? If we add a base, this proton is acidic due to the presence of the sulfoxide group. So base will abstract that proton. Negative charge will come here. That negative charge can attack over this benzyl bromide. Bromine will leave and here it will come this CH2, then phenyl, that is benzyl group. Then what can happen? Again this sulfoxide sulfinate rearrangement can happen because this allylic sulfone. So allylic sulfone can undergo the sulfoxide sulfinate rearrangement. So this oxygen lone pair will attack over this position. This double bond will again come over here and this will be breaking. So that will give rise to this compound. Here methyl group and here OSPH will be there. Double bond will come over this position and here it will be CH2 and pH. Then if we use any proper reagents like to cleave this oxygen sulfur bond, it can give the corresponding hydroxyl group, that is the product. So this is sulfoxide sulfinate rearrangement, an application where two times that same type of rearrangement is happening. So here this is also possible through this one. So these are the possible intermediates. Moving to the last question of week 2 assignment. Yeah. So this compound is represented as 12I5, 12I7, 10I5, 10I4. So which is the correct representation for this compound? So this is basically iodoxybenzoic acid, 2-hydroxybenzoic acid, IBX, which is the oxidizing agent. So here the correct answer is option 4. We call it 10I4 because as we can see there are in total 1, 2, 3, 4 bonds attached to iodine. That's why this 4, I4, it is coming from 4 bonds attached to iodine. But if we see the electrons, how many electrons are there? 2 from this bond, 2 from this bond, 2 from this bond, 2 from this bond, 8, and then 1 extra lone pair of electrons. So 2 from each bond and extra pair of electrons, that is total number of 10 electron. So that's why it is called 10I4. 4 bonds are attached to iodine and it is a 10 electrons around this iodine. So that is about the week 2 assignment. So I think we can stop here for today. Maybe next session we can have the discussion of week 3 lecture contents and some more problems. If you have any questions, doubts, or any other comments, you can tell. Okay, if there is nothing else, we will stop here. So thank you for joining this recorded session, this recording of the session, and this slides will be made available for you. Yeah, so see you in the next tutorial session. Okay, thank you everyone. Thank you for joining. If there are no questions, you can leave.
Thank you, ma'am.
Yeah, thank you.